Continuing with gas laws, we will now cover Charles' law, Gay-Lussac's law, and degrees Kelvin. Charles' law. For any gas at a constant pressure, the volume of the gas will vary directly with absolute temperature. There's the formula on the right. V1 over T1 equals V2 over T2. Gay-Lussac's law. For any gas at a constant volume, the pressure of the gas will vary directly with the absolute temperature. There's a formula. P1 over T1 equals P2 over T2. Okay, we're going to just go in a bit of history here of these laws. In 1787, Jacques Charles, a Frenchman, he was actually a chemist and a scientist, proposed volume and temperature relationship with his work in hydrogen balloons. In 1802, Gay-Lussac, a French chemist, refined Amonton's law of 1702 and published pressure-temperature relationships, highlighting Charles' work earlier. In 1848, Lord Kelvin, who defines absolute zero, which is degrees C minus 273. So he was a British mathematician and a physicist, and he defined the theoretical point at which all molecular motion ceases. Okay, let's look at the diagram. In this diagram, we see in the middle the combined gas law. And then at the four corners, we see P, V, T. P being pressure, V being volume, and T being temperature. Okay. If we look on the right-hand side there, we see Charles' law. Now, that's derived from combined gas law simply by removing P1 and P2. We're only concerned about volume and temperature with Charles' law, so that's simplified it. Likewise, with Gay-Lussac's law, on the bottom left, we can see that that is associated with pressure and temperature. So that gives us P1 over T1 equals P2 over T2. Okay, we're going to do an example using a diving bell from the surface, lowering it down to 3 meters. Okay, but before we do that, we'll just go reiterate what we've been talking about. In Charles' law, if temperature increases, volume increases. If temperature decreases, volume decreases, providing we have constant pressure. Okay, the volume must always be in litres or cubic meters. The temperature must be in degrees Kelvin, which is degrees C plus 273. Try and get that number stamped inside your brain. You're going to be using it a lot. The formula again for Charles' law, V1 over T1 equals V2 over T2, and that's derived from the combined gas law. So here's the example of the Charles' law equation using a diving bell. Okay, we're going to do an equation based on Charles' law. Okay, here's the question right here. It's a hot day. It's 40 degrees. The bell on the surface is also 40 degrees inside the bell. The bottom bell door is up, which means it is not sealed, which means pressure is not controlled. We lower the bell into the water, temperature is 10 degrees, so now the temperature inside the bell is 10 degrees. We've gone from 40 to 10. The bell volume is 6.03 cubic meters inside the bell. What's the new volume? We've gone from 40 to 10, we've gone from 6.03. What is the new volume? So we're seeking V2 as the unknown variable. Okay. Gas in the bell contracts. We know it's going to contract. Now, the bell volume 6.03, we've gone from 40 to 10. Now, that's in degrees Celsius. We need to convert that to degrees Kelvin. So here we go. 40 plus 273 is 313.
10 plus 273 is 283, okay? We're going to use that a bit later. But let's figure out the formula first. V1 over T1 is equal to V2 over T2. That's our formula. Now, we must ensure that the unknown variable is all by itself, and we also have to make the unknown variable the top of the equation in order to solve this, okay? So in order to do that, we must take 4 steps. Step 1, cross multiply. Cross multiply the equation, put T2 over here, T1 over here, and we get this. V1 times T2 equals V2 times T1. That eliminates the denominators at the bottom of the equation. The next step, we must isolate the unknown variable by dividing both sides by the term next to the unknown variable. That's the term next to the unknown variable. So we have to divide both sides by T1. The next step, we have to simplify the equation by cancelling any common terms above and below the equation. So the common term above and below is T1. Cancel those out. Then we invert the equation this way, and it gives us V2 equals V1 times T2 over T1. That completes that calculation for finding out how to do the calculation, I should say. Okay, there it is right there. Now there's a quick way to do this. It's another way of doing it. I'm just going to show you quickly before we punch in the numbers. So if we look at the unknown variable, and right below it we have T2. If we multiply both sides by T2, that will help us to get to this equation. So multiply both sides by T2, and once we've done that, we need to then cancel out the T2 on the top and the bottom of the equation, there, and that will give us V2 equals T2 times V1 over T1, which is this right here. So there's 2 ways of doing it. Try to learn both methods. If you get involved as an LST or a supervisor and you find yourself doing these calculations more often, you'll end up needing to know the quicker version. Let's punch in some numbers. Okay, there's our volume, 6.03. 283 is the 10 degrees Celsius. So we multiply the volume times 283, and 313 is the 40 degrees. So we volume times the new temperature divided by the old temperature gives us 5.45 cubic meters. That's the new volume of the bell, which is 10% shrinkage. So there's your answer, 5.45. Now if we divide that by the original volume, we get 0.90, which means 10% shrinkage. Okay, we're going to do an equation based on Gay-Lussac law, and that is this equation here. P1 over T1 equals P2 over T2. Okay, so the example we've got is a Bailert bottle at 200 bar on the surface. We've got a temperature of 30 degrees Celsius on the surface, on the bottle. What will the pressure be when the temperature drops to 4 degrees Celsius? Okay, we've got the steps on the board here. Step 1, cross multiply. We have to cross multiply the equation to eliminate all of the denominators. Cross multiply here, get rid of the denominators, gives us this. P1 times T2 equals P2 times T1. P2 being the unknown variable. Okay, next step. Isolate the unknown variable by dividing both sides by the expression next to the unknown variable. Here we go, we divide both sides. Okay, next step, simplify by cancelling any common terms that appear in both the top and the bottom. There we go, T1, top and bottom, cancel them out, and it gives us this. Okay, so this is P2 equals P1 times T2 over T1, and the numbers tell us 200 times 277 divided by 303, and that gives us an answer of 183 bar. So we've dropped from 200 bar to 183 bar. as the temperatures drop from 200 down to 100, from 30 degrees down to 4 degrees. Okay, I'm going to do another example. This time we're going to use the FPS system. What is an FPS system? FPS system is foot, pound, second. The other system is meter, kilogram and second. Some people call them imperial and metric. So with the FPS system, we use Rankine instead of Kelvin. With Rankine, we add 460 degrees when we do calculations. So we have a 3000 psi bailout bottle with a temperature of 100 degrees Fahrenheit. What will the temperature be when the temperature drops to 40 degrees Fahrenheit? Okay, so let's look at the different criteria. We've got 3000 psi, P1 is 3000 psi. T1 is 100 degrees Fahrenheit. So we add 460, gives us 560 degrees Rankine. T2 is 40 degrees. So we add 460, gives us 500 degrees Rankine. Okay, so let's use the quick method here. P1 over T1 equals P2 over T2. If we multiply both sides by the expression under the unknown, that gives us, have a look at that. Okay, now we need to cancel the common terms that are both above and below on the same side of the equation. Okay, therefore P2 equals P1 times T2 divided by T1. So that means we've got 3000 times 500 divided by 560 gives us an answer of 2679 psi, which is about 300 psi less. So there's our answer.
Okay, we're going to continue with Gay-Lussac's law here, just to give a bit more practice, okay? So just to reiterate, if temperature increases, pressure increases. If temperature decreases, pressure decreases, providing we have a constant volume. Okay, so the pressure must be absolute pressure and the temperature must be in degrees Kelvin, which is degrees C plus 273. It's derived from the combined gas law, and we use that formula. P1 over T1 equals P2 over T2. This is Gay-Lussac's equation. Okay, step one. Unknown variable is a numerator, top of the equation, P2. Okay, we need to cross multiply the equation to eliminate all the denominators. Once we've cross multiplied, we get P1 times T2 equals P2 over times T1, P2 being the unknown variable. The next step, we isolate the unknown by dividing both sides by the expression next to the unknown. The expression next to the unknown is T1, therefore we divide by T1 on both sides of the equation, and then we simplify the last step by cancelling any common terms that appear in the both above and below the equation. So that is a T1, it's above and below. You can see there T1 above and below on the right of the equation there. If we cancel them out, we then can see it's P2 equals P1 times T2 over T1. But by placing P2 on the left-hand side of the equation, it looks a lot tidier. Okay, now there will be times when you're doing these calculations where you need to do the full combined gas law. You can't do Charles' law or Gay-Lussac's law equation. You must do the full combined gas law equation. And here's an example right here. So if we had the initial absolute pressure of 1099 psi and we had a volume of 13 litres and a temperature of 0 degrees. Now the second absolute pressure was 2903 psi and a volume of 5 litres. What is the unknown variable? What is the second temperature in degrees C? So, as we've done before, we have identified the unknown variable. In this case, it's T2. Then we cross multiply. So we get P1 V1 over T1 equals P2 V2 over T2. When we cross multiply, that becomes P1 times V1 times T2 equals P2 V2 times T1. Okay, next step, we need to isolate the unknown. So by dividing both sides by the expression next to the unknown. In this case, the expression next to the unknown, next to T2 there, is P1 V1. So we have to divide both sides by P1 V1. So as you can see there, the equation is growing. Now, in order to simplify this, we can then cancel out the common terms. So simplifying it, we cancel out P1 V1 on the top and P1 V1 on the bottom on the left-hand side of the equation, and that gives us T2 equals P2 times V2 times T1 over P1 times V1. And we bring the P2 across to the left-hand side, which tidies up the equation, makes it easier to read. So T2 equals P2 times V2 times T1 over P1 times V1. Now let's punch in the numbers. The same equation from the previous slide, the same information. We're not going to go over it again. We're going to go straight into the calculation. So input the values. 2,903 psi divided by 14.7 gives us 197.48 atmospheres. So if we put that in the top left of the equation there, we can see in place of P2. And if we've got 1,099 psi divided by 14.7, gives us 74.76 atmospheres absolute. Okay, so on the bottom left, we've got P1, which is 74.76, times 5, which is at the top of the equation in the middle there, times 273, and on the bottom we've got times 13. Okay, if we do the calculation, that gives us 269,560.2 divided by 971.88. If we do that again, the next step, and then we subtract by 273, that gives us 4.36 degrees. Have a practice of that. Okay, in summary, Charles' law. For any gas at a constant pressure, the volume of the gas will vary directly with the absolute temperature. Try to remember V1 at the top of this equation. V1 over T1 equals V2 over T2 for Charles' law. And for Gay-Lussac's law, for any gas at a constant volume, the pressure of the gas will vary directly with the absolute temperature. There's our formula. P1 over T1 equals P2 over T2. And lastly, combined gas law. There will be times where you must use the full combined gas law, also known as the general gas law, where instead of the 4 variables, you are using 6 variables. On these occasions, follow the same algebraic principles as we've already explained.